So I said that this is a degenerate electron system. Okay, what does that mean? Well, you remember from when we talked about it being a degenerate electron system in the core of the sun, this is not like an ideal gas. If you add mass to it, you're adding energy. If you add energy to it, then you're allowing it to have the ability to shrink closer together because you're allowing the energy levels to overlap. No two electrons can have the same energy level, energy state, or quantum numbers if they can interact with each other. And so if you have enough energy, you can have a bunch of these electrons at higher energy, and then the atoms can get closer together. And so at that point, that means that you'd be smaller. So the interesting thing is, if you increase the mass, then this thing will actually shrink smaller. Okay, now that's weird. Okay, a white dwarf, the sun's going to turn into, which is about half a solar mass. It's going to be a little bit bigger than Earth. About one solar mass is close to the size of the Earth. A little bit more mass is smaller than Earth. So the more mass you have, the more compact it is. And so there's a relationship here inverse to the mass. In fact, technically, it's close to inverse to mass to 1/3. Okay, so the bigger it is, the more mass it has, the smaller it gets. Okay, now, when you get very far up here, like around 1.3 solar masses, then that equation no longer holds properly, and the thing starts diving off a little bit. Okay, the biggest mass that a white dwarf can have turns out to be about 1.4 solar masses. We call that the Chandrasekhar limit after a fellow by the name, an Indian astrophysicist by the name of Chandrasekhar. And so Dr. Chandrasekhar came up with this idea that the degenerate electron pressure is only able to hold up so much mass. He worked out the mathematics of that, and it's 1.4 solar masses. At that point, if you exceed 1.4 solar masses, then your white dwarf is going to shrink and shrink and shrink. Basically, you're going to have enough energy, you can shrink the thing all the way together so that all the atoms essentially overlap each other. When that happens, then it becomes impossible to maintain separation between neutrons and protons. And the electrons are all going to be mixed in there as well. You're going to have so much energy, you're going to actually create a nucleosynthesis event in which you basically get rid of all the protons and electrons, and you end up with just neutrons. Okay, we call such a thing a neutron star. Now we'll get back to that later because that turns out to be a very simplistic explanation as to what happens there. But you'd shrink basically down to something about the size of a giant atomic nucleus. Now, by giant atomic nucleus, I mean about the size of the city of Arlington. Okay, so, but the Chandrasekhar limit, 1.4 solar masses, is the biggest mass that a white dwarf can ever be. Now, important thing to note is this is the white dwarf size. It's not going to be the size of the original star. It's what's left after everything has happened. So this graphic right here shows a 0.4 solar mass white dwarf is bigger than Earth. About 0.8 solar mass, you get the size of the Earth. 1.2, quite a bit smaller. A little bit more than that, about 1.25, you get down to about the size of the Moon. Okay, and then as we go, it gets smaller and smaller and smaller, and then the threshold is 1.4 solar masses, the Chandrasekhar limit. But a star that's 1.5 solar masses to begin with will still give you a white dwarf because it's going to lose so much mass when it's a red giant and when it's making a planetary nebula. Even a star of 3 solar masses will lose enough mass, you get a white dwarf left. You can even get a star of 6 solar masses. It will actually go on and fuse additional stages and fuse into neon, in fact. But it will still give you a white dwarf. It will lose so much mass. Remember, the red giant wind can lose a huge percentage of the mass of a star, and then the planetary nebula can blow away all the outer layers. That's another huge amount of mass. If what's left is less than 1.4 solar masses, you get a white dwarf. And so calculations show that you can go all the way up to 8 solar masses, and still what's left is barely 1.4 solar masses. And so that would barely give you a white dwarf. All right, so that means that any star that's less than 8 solar masses, initially, it's going to be less than 1.4 solar masses left over after everything is done, and so that means it's going to be a white dwarf. If it's bigger than 8 solar masses, it's going to go further, and it's going to shrink down past a white dwarf into a neutron star. Okay, but less than 8 solar masses, that gives you a white dwarf. How a star dies depends greatly on the initial mass. How a star lives depends on the initial mass. So all the stars start as a cloud of gas in a globule, creates a protostar. You know, stars that are between 0.4 and 8 solar masses, they live out their life in the main sequence, expand to be a red giant, shrink a little bit, expand to be a bigger red giant, or sometimes we call it a red supergiant, blows outer layers off into space, makes a planetary nebula, and then leaves behind a white dwarf. Okay. Stars that are about 0.08, less than 0.08 solar masses, they just go straight to a brown dwarf. They never actually become a white dwarf. Okay, they never actually become a star either. Okay, they become a brown dwarf. Stars bigger than 0.08 solar masses, they become a little red dwarf star. Get all the way up to about 0.4 solar masses, it's still a red dwarf star. Okay, and so far none of them have died. The universe is not old enough for anything that small to have ever died. We think that they probably avoid a lot of these steps. They probably don't go through the planetary nebula stage. They don't blow their outer layers off into space. The core probably fuses into helium, but never starts fusing into carbon. So you end up with a helium degenerate core in the middle of a hot cloud of hydrogen gas surrounding it. That's our best guess as to how they die based on calculations. But as I said, we've never actually seen one die because the universe is not old enough for that to happen. But between 0.4 solar masses and 8 solar masses, what's left will be less than 1.4 and will be a white dwarf, 1.4 solar masses.